I get 1 equals x, don't I? I agree. But what about 0? 0 works, right? You lost your solution. Why? Because you divided by x. And when you divide by a variable, you eliminate the possibility that that variable could be 0, right? So this is, I remember I learned this very late, and I was kind of like, shit, this whole time, man, I would have divided by x. That's what I would have done. And then I realized later, I guess, I don't remember when, but crap, you actually have to move everything to one side. Then you factor out a GCF, and then you set both factors to 0, and you get both solutions that way, as opposed to dividing. So just be careful on something like that. And does this agree? X equals 0? Yes. X equals 1, right? So we get our two solutions here. All right, back to the area. I'm going to go integral. Because this is area, I'm going faster. I'm going to go a little slower through these next ones. What's it going to go from? Integral from 0 to 1, right? Those are my left and right. Right? I'm doing a little rectangle in here. I'm moving it left and right. Okay, and then what? Function on top, which is x, minus function on bottom, x squared, dx, done, move on. All right? That's the answer to part A. I'm not working these out, right? Because we could do that. Okay, find the volume if we rotate this about the x-axis. This should work pretty much the same, shouldn't it? It should go, what's the only difference in our integral? Pi, 0 to 1, right? And then what? X squared minus x to the 4th power dx. So all you're doing is you're squaring each of these, right? Be careful. You do not square the whole thing, right? You don't just take this and square it, because that's not the same thing. You square each one, that's the formula. And then the pi. So these two, pretty clean, yeah? Would you agree? Pretty clean? Pretty clean? All right, what about going about the y-axis? What about going about the y-axis? Well, to go about the y-axis, we actually have to change our rectangle, don't we? We have to actually move this and turn it sideways. And then we have to rewrite these as functions of y, not x. Okay, we can do that. Let me just redraw it. New picture. I'm in no hurry. Here we go. Here we go. Got my parabola. Got my line. Okay, let's start with the line because that's the easier one. Can you solve this equation? Y equals x for x? X equals y? Yeah, same thing, right? It's just backwards. X equals y. So this is a function of y now. Now this one up here that was previously y equals x squared, to solve for x I have to take the square root, which means I'm going to have plus or minus, right? And we're going to take the positive one. Now why are we going to take the positive one? So square root both sides, we get root y. Because when I'm looking at this curve, right, over here, my x's are positive, aren't they? And my y's are positive. So if I would have used a negative here, then that would have given me the other side, because that would give me negative x values. So that will take care of this part. Now, when we do this formula, we're not going to say top and bottom anymore, right? What are we going to say? Right and left. So for part C, I'm doing a volume, right? Not an area, doing a volume. So this should be pi integral where to where? Do we know where these are? Yeah, well, we know this is still 0, right? And this hit at 1, didn't it? And if x is 1, what's y? 1. You could do that by plugging it into here or into there. It doesn't matter. If x is 1, y is 1. So the integral goes from 0 to 1 still, right? And then it's going to be, you said not top, bottom, you said right function squared minus left function squared. So right function is the root one, right? That's this one. What happens if we square that? Yeah, I'm going to do root y and then put squared here. And then minus this one right here, written in terms of y. So y squared. Agreed? And then all of that dy. Okay? I want you all to notice something, if you can. This right here squared would be y, right? Yes. I put that up there intentionally so you would know where that came from, but this is really just going to be y, right? Are these two going to give you the same answer? They should not. Because this one, what do? You find the antiderivative, which would be 1/3 x cubed minus 1/5 x to the 5th. You plug in 1, you plug in 0. That's going to give you an answer, right? Here, you do the antiderivative, 1/2 y squared minus 1/3 y cubed. You plug in 1, you plug in 0. That's going to be a different answer than this, right? It should be. Which means revolving this region around the x-axis gives you one volume. Revolving it around the y-axis gives you a different volume. Okay. So those first three don't require too much, I guess not too much. Is that all right? You kind of follow that? All right, let's now do part D. And for part D, I'm going to start with a whole new picture. So for part D, I'm rotating it about y equals 5. Okay, so here's my picture. Got this, got my little parabola in here. This time I'm going to do it this way. I'm just going to do just the part of the parabola that I need, and then just the part of the line that I need, like that. And now I need to include the axis of rotation, where I'm rotating it about. And it's 5, isn't it? Y equals 5, which is somewhere up here. I'm rotating it around that axis. So we're going to take this like that through the board, around the other classroom, come back, boom, there's our solid. What's its volume? So what did I say the formula for this was? It was like integral blah, 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 pi, right? Pi, integral, some. Then r out squared minus r in squared, right? We have to determine what our outer radius is and what our inner radius is. Y'all ready to do that? This is the trickiest part. So I like to do this. I like to draw my x-axis. I like to draw my axis of rotation. I like to come in here and draw my little rectangle in here. And here's my little rectangle that I'm about to rotate, right? I'm going to rotate that little rectangle around. Okay, that's my little rectangle right here. I'm also going to put a little label here. My red function's up here. My blue function's down here, right? Now, imagine that you are standing on the axis of rotation, just hanging out, okay? And you're looking out, and you see the rectangle on the ground, right? You see it out there? You're trying to find the distance from you to that outer part of the rectangle. So what we need here is this distance from here to here. That's my r out, right? And then the distance from here to here is my r in. So let's figure out what they are. What's my r out? Look at it. Think about it. What is the distance from here to here? 5 minus x squared. 5, let's see why. What's the distance from here to here? 5. So it's not bigger than 5, right? It's 5, but then you have to take away this much, right? What is that distance right there? X squared. That's the blue curve, isn't it? So if the distance from here to here is x squared, and the distance from here all the way to here is 5, right? Then if you take 5 and subtract the x squared, you get the r out. Do you all see that? This is important because this is what I want on the test. I need you to be able to see this part, because that's all I want you to do is set up the integral. I don't need you to compute it. Are you sure? What about the inside radius? 5 minus x this time, because this distance from here to here, wow, that's bad, x, right? And then the whole thing was 5, so you take 5 and take away x, and you've got 5 minus x, right? Yes?
No, I'm just thinking about what that question mark is. So the question mark after, when you were saying earlier, r out squared and then d question mark?
Yes.
Would the question mark be related to the x and x squared?
The question mark, what you're saying is that dx, dy, which is it going to be? It all depends on the way we drew our rectangle to start the problem. Look at our rectangle, right? How wide is it? Well, that's a measurement in the x direction, right? So it's going to be dx. If we were, if our rectangle was like that, and these were functions of y, not x, then it would be dy. All right, I think we're here. The volume of this would be pi. We're integrating now. Our rectangle's moving from where to where? Which is going to create all these washers, right? Yeah. That go around this thing. So 0 to 1 still, right? And then we have what? The outer radius, which you said was 5 minus x squared, but squared, right? 5 minus x squared squared minus 5 minus x squared. And then, yeah, dx. I'm just going to put it like that, dx. So if we had to compute that, right? If we had to compute that, we could do that. We could square that out, collect any like terms we might have together. Power rule, just do them one by one, right? What do y'all think? Does the picture help? Yes. Picture help you see it? Out, in, R out, R in? Yeah. Okay, let's do the last part, part E. And we're rotating around y equals what? -2. So, yeah, I'm going to start a whole new picture. All right. Forgot what I was doing. All right, so here we go. This, parabola, this, a little line guy right here, and -2, so that's like down here. That's my axis of rotation. I'm taking this little rectangle, wrapping it around, which is going to create all these little washers. So on the side over here, I always start by just extending my x-axis out here. I put my rectangle up in the position that it's in, which is somewhere around over here. And then I put my axis of rotation down here. I'll draw these little arrows because they're, I just picked up this marker today. It's dead. It's dying. All right.
Sorry, once more, just to remind myself. The outer is the parabola? Yeah.
The outer is always the distance from the axis of rotation, as if you were standing here, to the outer edge of the rectangle.
So that would be the x. As far as our outer and our...
It's going to involve the x function, but it's not x. This distance from here to here is your outer radius. Okay? Standing here, looking out, saying how far is it from here to here? That's your outer radius. Your inner radius is the distance from here to the bottom edge. But then you actually have to compute how far, like that distance. So So what is the distance? Let's do r out. What's the distance from here to here? If I asked you to grab this end of the measuring tape and start walking out over there, right? What would be the distance from here to here? 2, right? 2. And then you would walk out how much further? Well, no, to the top edge of this, right? And that top edge is the red function, right? Which is x. So it's going to be 2 plus x. Got it? 2 plus x. So r out is 2 plus x. And then what's the inner radius? From here to here, 2 plus x squared. That make sense? All right. We're still going to integrate from 0 to 1. It's still going to be dx. And we're going to have pi out front. Pi, integral, 0 to 1. Outer radius, 2 minus x, or 2 plus x, sorry, squared, minus inner radius, 2 plus x squared, squared dx. And again, you could expand those out, figure out what they are, and then integrate term by term. So we wouldn't need any techniques of integration for this, would we? Yes?
Just a quick question. So, the set of the intercepts that we get, so for example, in this case, 0 to 1, is it always going to stay the same, or are they going to vary from problem?
Is it always going to be 0 to 1?
No, like, so let's say, for example, in this problem was 0 to 1 at the beginning, correct?
Yes.
Let's say we get another problem that's going to be 2 to 3.
Yeah, 2 to 3.
It's going to stay the same throughout the same?
It'll stay the same every time you're going around the x-axis or any line that's horizontal. Because your rectangle, like imagine if I go around the x-axis or a line up here or a line down here, would you agree that my rectangle is going to move left and right? Yes? So it's going to be limited by my x values here. So if it's 0 to 1 or 2 to 3, that's never going to change. Now, when we wrap the other way, this way, then we would, because we have to lay the rectangle down sideways. How do y'all feel?
Makes you wonder how, like, the other professors would do it. You draw a little rectangle to the side would kind of help with the measurement.
I think everyone does it different.
Oh, yeah.
Yeah.
I'm curious, because I had Mr. Cope for Creek's house, I was wondering how.
Some people translate the graph. So they take the graph and instead of doing that whole out-in thing, they just say, okay, what we're going to do is we're going to shift our axis of rotation and the function. We're just going to move it all up 2 or all down 5. And all it is a translation of your graph. Some do it that way. I don't. I believe this is more constructive visually than it is to do a translation. That's just my opinion. All right. Okay, so look. I have a particular problem that I'd like for us to look at that I want to see what you think about this. This is y equals sine x. Okay? And I'd like for us to just focus on the part of the sine curve, this first arc that goes, what is this value again? Pi. And this is 0, right? Yeah? Ladies, you all good? Okay, that's all right. We found the area of this, didn't we? We did. I believe if you look back, it's 1. The area of that was 1. And I thought it was pretty awesome that that would be 1, and no one else thought it was awesome. All right, so let me ask you this. What would be the volume? What would be the formula if I wanted to know the volume of that wrapped around the x-axis? Let's see if we can do it without writing anything down. What would be the volume of this object if we wrap this around the x-axis? What would be the formula? Ready? Here we go. Pi, integral, 0 to pi, sine squared x minus 0 dx. So you just have to integrate sine squared. Can you integrate sine squared? Power reducing formula? Remember that? Okay, so we could wrap that around the x-axis. Yeah? Can you wrap it around the y-axis for me? What do you mean you have to change it?
We'd have to come up with like 2 parts between right and left.
Okay, so I agree that integral would be from 0 to 1.
But we don't have a clear right function and a clear left function.
Okay, so when we were here, when we do it around the x-axis, listen to my language here because this is kind of new, or I've said it, but I'm really going to emphasize it now. When we were doing this around the x-axis, right, my rectangle was perpendicular to the axis of rotation, right? So when we're doing washers, right, washers, that's the method that we've been doing. That method, your rectangle that you're going to rotate is always perpendicular to the axis you're going around, right? Okay, so if I'm going to use washers here, and this is my axis of rotation, then my rectangles need to be perpendicular, which means my rectangles would have to come this way. Agreed? That's a problem. Because your top, well, we didn't call it top and bottom, we called it what? Right and left? They're the same freaking curve, right? And there's not an easy way to break it up. If this were a parabola, we might be able to get away with it because we could do some square root functions and maybe be able to hack our way at it. But because it's a sine function, it's not easy to break this down. Does that make sense? It's not easy to find the top and the bottom because they're technically the same function. You have to solve that for x. What happens if you solve this for x? What do you get on the other side? Arcsine. So you have an arcsine function now. Arcsine functions have domain restrictions, don't they? Like what? What's the domain restriction of arcsine? Drum roll. Negative pi over 2 to pi over 2. And look where we're looking. We have trouble. This is trouble, yes? So because this is trouble, we have a new method. Don't get freaked out. It's beautiful. It's great. Okay? So I'm going to show you the new method, but I'm going to show it to you abstractly first. So we'll get back to this. We'll get back to this. Okay? So do you see when you would run into a problem? When you're trying to go around an axis, but when you draw your rectangle, the top and bottom of it or left and right of it happen to be the same curve. So let's say we have this happen. Let's say that we have a curve like this. Let's call that F. And let's say a curve like this, which we'll call G. So everything look familiar here already? I mean, this is all familiar, right? We have a top and a bottom function. This time, we want to wrap around the y-axis. So we're trying to wrap it this way. Do you see how problematic it is? Right? When you turn, you draw your rectangles in here. That rectangle right there hits F in 2 places. The rectangles down here hits G in 2 places, yeah? So this is the problem. Is there a way that we can get through this still? Let me also label this A and label this B, okay? Trying to go around the y-axis. The only thing I'm really comfortable with are these darn vertical rectangles. I love these vertical rectangles. You know, it makes perfect sense for a problem like this to say F minus G. I want to continue to say that, right? What would happen, just for the hell of it, what would happen if I wrapped that rectangle around the y-axis right now? What would it look like? So can you see it going like this? Around. It's not a washer anymore, okay? Like a tube, okay? So can you see that if I did that, it would go around Now my y-axis is down here, but would that be the shape you see there? That's just that little blue one wrapped around, yes? If I could figure out a formula for the volume of that, if I could find a formula for the volume of that, then all I would need to do is move this rectangle left and right, do an infinite number of those, and add them all up, right? This is the same process we did with washers, except that we're rotating and we're not getting a washer anymore. We're getting this shape. We call this, by the way, a shell. I don't know, that's what we call it, a shell, right? So this is actually called the method of shells, but who cares about that right now? We wrap that around. If I can come up with a volume for that, then maybe I can just add them up with an integral. Do we know the volume of this, though? Yeah, so you know what? I want to show you what I'm trying to do before I actually finish that. Where is it? See if you can see this. Okay, so basically what I'm doing is I'm taking a function, trying to wrap it around the y-axis. Can you all see the y-axis here? The y-axis is here. Here's my function. If I try and do rectangles this way, it doesn't work, right? So I'm instead drawing my rectangles like I like to do, and I'm wrapping each of these around the x-axis. I mean the y-axis. And let's do it. Let me just do a few of them, not so many, just a few rectangles. And then, nope. And this is not very good. Well, you can kind of see this. You can kind of see it. Do you see that if I took one of these rectangles and wrapped it around, I'd get this like thing right here? But it comes all the way around in front. Yes? And if I did more rectangles, an infinite number of rectangles, I'd start to get a better idea of what this looks like. Do y'all see that? Kind of. And then if I could do an infinite number of them, essentially what I'm doing is wrapping those around, and I'm getting this bundt cake, half a bundt cake in this case. But do y'all see that? And now it comes all the way around also, but just for visualization. So instead of doing a bunch of washers and adding them up, I'm doing a bunch of these shells and adding them up. Make sense? Yeah. The key to this method is that washers, your rectangles were perpendicular to your axis of rotation, right? With this method, it appears that my rectangles can be parallel to my axis of rotation, right? And that's what makes shells so great, is that we can use it in that case. So back to my picture, got F here, got G here, got A here, got B here. And then I wrap this sucker around, there he is, wrapped it around, and I had this. And I asked you if we might be able to come up with a formula for the volume of that, right? All right, so here it comes. I'm going to get my magic scissors first. My magic scissors are going to cut this thing, all right? I'm going to cut it. I'm going to lay it flat. So if I do that, it now looks like that, doesn't it? Cut it, lay it flat. Agreed? Now this is like a box, right? Volume of that's length times width times height. Okay, let's talk about this distance right there. What's that measurement right there? Well, that is this, and that was this, right? Wrapped around. So isn't it that width? What's that width? dx. We've been calling it dx the whole time, right? This is dx. All right. How about how tall this thing is? That is this, which we've done that before. What's that? Distance from here to here.
Is that the RLs?
That's just f minus g. That's just the f function minus the g function, right? So this is f minus g. This is the hardest one right here. What is that distance?
The y-axis to the power.
2 pi r. What the hell are you talking about, 2 pi r? What's 2 pi r? If you have a circle, right? If you have a circle, which we had here kind of like this, right? And we cut it and we lay it open like this. The distance from here to here is the circumference, isn't it? Circumference of a circle is 2 pi r. 2 pi r, I agree, but what's r? R is the distance from here to here, right?
Yeah,
Which is for us the distance from the y-axis to not A, not B, to the rectangle, right? To the rectangle. And what is that distance? Well, we haven't ever talked about it, have we? The distance from the axis of rotation, y, to our rectangle is x. Because x in the problem is going to vary between where and where. When we integrate, we do our summation. We're letting x go from where to where? From A to B, right? So if I draw an arbitrary rectangle in here, that distance from here to here is the x coordinate exactly. It's from here to here, isn't that x? So this is 2 pi r, but the radius is actually x. And this is a formula. The volume of this slab right here, the volume of that little slab is 2 pi, and then what? X times these two subtracted, f of x minus g of x, and then what? Dx. And that would give us the volume of one of these. Now we need to add them up, right? An infinite number of them. So if you want to take this and wrap it around the y-axis, the volume of that solid would be, you help me. Okay, we can pull a constant out here. 2 pi this time, right? Not pi. For this method, 2 pi comes out. 2 pi integral from a to b. So a to b is still where we're going to let our rectangle move from. We're going to let it move from a to b. We're going to let our x vary from a to b. So a to b, and then the rest of the formula. X, f of x minus g of x dx. Yeah, this x is just sitting out here next to it. Now, remember, you can't pull the x out because the x is a variable, so you have to leave it there. Do you believe this formula? Do you see how I came up with it? It's pretty nice, right? That's a pretty cool approach to do it like that. So when would you use this method over the other method? Let me tell you. When you're trying to wrap something around and things aren't working out, and so you have basically your axis of rotation, and the rectangle that you want to use is parallel to it. That's when you use this method. When you're wrapping this way, like around the x-axis, you're perpendicular. We would like to use washers in that one, not this one. So this is called method of shells. The other one's called method of washers. Yes?
Even when we find out eventually what x is going to be, we still don't pull it out.
When we find out what x is eventually going to be,
So like later out, so like when we start playing in the values and we find out what x is, we keep it inside the interval.
we don't plug in what x is until after we do the antiderivative,
Okay.
right? So that it's afterward. So let's go back to that problem with sine. I asked us to take this y equals sine x. I asked you to look at it between 0 and pi. I asked you if I asked you to wrap that around the x-axis, everybody sat there and told me exactly how to do it, right? Pi integral 0 to pi of just the function squared, right? That's around the x-axis. But around the y-axis, I'm going to say, all right, well, I've got to go here, right? I'm running it. It's parallel to my axis of rotation, so I'm going to use shells. So that means the volume of this is going to be 2 pi automatically, integral. Now my variation on my x is going to go from where to where? 0 to pi. And then it's going to be x, which is just x, right, times the upper function, top function, minus the bottom function, which is 0. So just x sine x. And how would you integrate that? Integration by parts. Right? So, but that could be done. Okay. It's a lot, right? I mean, there's a lot of stuff here. And we're not done. We're still in this section 7.2. We still have one more thing to do. But it's a separate topic. It's separate but related. It's not going to have anything to do with rotations anymore. We're going to do something else. So what I think we should do is probably call it a day. And I think what you should work on is the homework for 7.2. Everything, but do not worry about, I believe, number 38. Is number 38 in the homework assignment? Yeah. 38 and 39? Yeah, don't worry about 38 and 39 yet. But try to see how you do with the other ones. I would say, I don't remember on my solution videos if I took the problems the whole way. I think I did. Like I went all the way with them. Are we good? Okay. Y'all have a good weekend. I'm just going to turn my camera off real quick.